Hey everybody, this is going to be another short unit. We're in Unit 6 and there's only one standard in this unit. That standard is to determine the solution set of rational equations and inequalities. And this is our first video. So we're going to be reducing rational expressions and finding restricted values. So let's go ahead and get started. What is a rational expression? Of course we have to start here. So a definition of a rational expression is a ratio, which is a fraction, of two polynomials. That is, that we have a polynomial expression, for example 3x plus 7, divided by another polynomial expression, perhaps x squared minus 25. A ratio is a fraction. The polynomials are the expressions in the numerator and the denominator. The domain. Our domain of these expressions, and then the functions that we'll be working with after final exams, the domain is all real numbers except where the expression or the function, in this case it's an expression because I don't have an equal sign or an f of x, but this applies to the functions as well, is undefined. Now, where is this going to be undefined? Because that we're going to have to specify. We will always begin with all real numbers except, okay? Which we can just write as r, and then we write x cannot be, and then we get to put in the exceptions. But what are those exceptions? The exceptions are going to be where the denominator equals 0. That will make a fraction undefined. So we need to look up where is the denominator undefined, or where is it equal to 0? Because as soon as we identify that, we know what the restrictions are. So let's take a look at these three examples and decide where the denominator would equal 0. It doesn't matter what the numerator is, because when the numerator is 0 of a fraction, then the whole thing just becomes 0. But when the denominator is a 0, this is undefined. Okay, so just like slope, actually, if you want to connect it back to slope, when the 0 is in the numerator, the slope is 0, and the 0 is in the denominator, the slope is undefined. So that may make that connection for you as well. Okay, so let's look in this case. I would take this 2x minus 5 and set it equal to 0. That means that x will equal 5 halves. So my restricted value is x equals 5 halves. My domain is all real numbers, but x cannot equal 5 halves. Please notice the difference. This is a restricted value, this is the domain. Let's take a look at the second example. X squared minus x minus 12 equals 0. Well, in order to find where this equals 0, we're going to have to use one of our methods from our quadratic chapter. That is, we can use inverse operations, we can use factoring in the zero product property, or we can use the quadratic formula. The whole point of this is to determine where is the denominator equal to 0. This one is actually very easily factored, so I'm going to use the zero product property. So x equals 4 and x equals negative 3 are the restricted values. If I ask you about the domain, you would write all real numbers, but x cannot equal 4 comma negative 3. Or negative 3 comma 4, because I'm just stating a list of values that x cannot equal. But let's take a look at this last one. This one's very different because I have both x's and y's. Because I'm working with an expression right now, I'm going to be able to decide what the denominator is not allowed to be. And that doesn't mean that x will have to equal a number. An x can equal another expression. So I'm going to use the same idea and set the denominator equal to 0. In this case, x cannot equal 2y. The restricted value is anything that x is twice y. You may also write it that y cannot equal 1/2 of x. So either of these would be considered restricted values or restricted quantities. All right, now we're going to be working with putting these expressions into lowest terms. That is, we're going to be reducing. And we're going to start with what we cannot do. If I have an expression of x plus 14 over, let's say, 2x plus 7, you cannot reduce the 14 and the 7. You cannot do it. What you can do is look for common factors. Factors as in factoring. So you must factor, you must pull it apart before you're able to cross things off, because we're not crossing things off. We're trying to reduce a fraction. So once again, you may not just cross things off like the 14 and the 7 and just call it a 2. It does not work that way. If you do that, you're not demonstrating your understanding of rational expressions. Consider this: 3 plus 5 over 4 plus 5. This fraction does not equal 3/4 because you just crossed off the 5's. This equals 8 over 9, which is not the same as 3/4. So you may not cross off the values. This goes for x's as well, not just numbers. So in order to do this, we have to factor. After you factor, you can reduce. So I'm going to factor the numerator of this piece. The numerator of this piece will factor to a 2p, and I'm going to put a 4 here, and plus and minus 1. And you can use whatever method of factoring you remember, if that's the factor box, or if you want to multiply the first times the last and get negative 8p squared, and then come up with the split the middle, that's fine. And then I'm going to factor the denominator. So I'm not changing the expressions. I'm not manipulating anything except that I'm factoring it so that I'm able to see what can be reduced. Remember, factor, then reduce. So if I take out a GCF here, now I cannot factor into two different quantities because I don't have the structure that allows for that, but I can factor out a GCF of 5p, leaving behind a p plus 4. Keep in mind these problems are designed to be reduced. So I would say probably close to 99 out of 100 of them, you will find something in the numerator and the denominator that is the same. And here we found that the numerator has a p plus 4 and the denominator has a p plus 4. Now don't worry, it's not as though we just crossed off a 14 and a 7, excuse me. You did not do that. You did not just cross off things like the 5 and the 5 over here in the example, because this is multiplication, whereas above you were crossing off over addition. This is saying something times something divided by two others. So those two multipliers, these factors, can be reduced. That leaves me with 2p minus 1 over 5p. This is now in simplest form. Let's do the next one. I'm going to go ahead and factor the numerator, and I'm going to factor out a GCF of 3, leaving behind a 2 minus k. In the denominator, I'm going to factor a k minus 2 and a k plus 2 because that's a difference of perfect squares. And you might think, well, that 2 minus k and that k minus 2 are exactly the same, but they are not. They are opposites. And in order to represent opposites, we will reduce with a negative 1. So that negative 1 gets multiplied by the 3 that remains, and the k plus 2 also remains. And this is the lowest terms of that rational expression.